Welcome back to part 6 of Physics of the Atom, and we're going to deal with the release of nuclear energy. So yes, that's Albert Einstein on the front, and it says, we cannot solve our problems with the same thinking we used when we created them. So, the release of nuclear energy. Conservation of energy. What is the law of conservation of energy? Right. Now energy cannot be created or destroyed. It can only be transformed from one form to another. So Albert Einstein realized that mass was equivalent to energy, and this relationship was given by his famous equation. Do you know what that is? Does it start with E? Does it start with E? Yes, it does. It starts with E equal to mc squared. And that translates to E equals to m times c times c. Mass must be in units of kilograms. And c, which is the speed of light, must be in units of meters per second. And that gives us kilogram meters squared per second squared. And this represents joule, which means energy. Right, so keep that in mind. Whenever there is a mass in energy, whenever there is a change in energy, there is an associated change in mass. This also means that mass can be transformed into energy. In nuclear fission, which includes splitting a large nucleus into two small nuclei, we see this happening. A lot of energy comes out, and the mass of these smaller nuclei is less than the original nucleus, and this mass change leads to a large release of energy. So the large release of energy explains why the two daughter nuclei, or whatever amount of nuclei given off, has less mass than the original parent nucleus. Right? That explains it, because you have parent nucleus, giving off daughter nuclei, and which is less mass than the parent nucleus, and you got a lot of energy coming out. Right, so that's a lot of energy coming out. That explains the change in mass. So here it asks, how much energy is released during the nuclear fission shown in this equation? And it says here, use delta E equals to delta mc squared. Right? So we have to deal with it. I can't believe I actually put this question here. Okay, so it's going to take some time. And it's going to take a really good calculator. So what I'm going to do, I'm going to skip to this and come back to that. So nuclear fission power stations use the thermal energy released to heat water from steam into steam, which drives turbines. These are then used to drive generators, which produce electricity. The induced fission is caused by a neutron colliding with a large nucleus. During this process, several other neutrons are released, and these can be used to split other nuclei, releasing more energy and yet more neutrons. This process is called a chain reaction. How much energy would be released if 1 gram of matter were completely converted into energy? Well, this is much easier to work out. E equal to mc squared. So we have the mass in grams. So we're going to divide. So 1 gram would be I need my calculator. If we know that 1 kilogram equal to 1,000 grams, so therefore 1 gram will give us X. So we say 1 gram times 1 kilogram divided by 1,000 grams to give us X, and that should give us 10 to the minus 3. Right? Did everybody get that? Right, so we're going to use 0.001 kilogram times, what's the speed of light? 3 times 10 to the 8 meters per second times 3 times 10 to the 8 meters per second, right? So we know that this is 10 to the 3, so we could put 10 to the 3 right here, 10 to the minus 3, and we could work this out. So we have 10 to the 16 minus 3 will be 10 to the 13, 10 to the 13 times 9, because 3 times 3 is 9. So let's make sure we have that correct. So we have 10 to the negative 3 times 3 times 10 to the 8 times 3 times 10 to the 8. Right, so 9 times 10 to the 13 joules, correct. Alright, so that's how much energy will be converted. That's how much would be released if 1 gram of matter are completely converted into energy. 9 times 10 to the 13 joules of energy. So nuclear fission power stations use thermal energy released to heat water into steam, which drives turbines, and these are then used to drive generators which produce electricity. Induced fission is caused by a neutron colliding with a large nucleus. Oh, this looks like the same slide. Oh, it's the same slide. Okay, skip that. Now, arguments for and against the use of nuclear power. For, the costs are low, right? That's the argument for using the nuclear power plants. Costs are low. Running costs are low. Only a small amount of waste is produced. Large supplies of nuclear fuel are available, and no carbon dioxide is produced, so no contribution to global warming. The arguments against nuclear power: commissioning, building, and decommission dismantling costs are very high. The nuclear waste contains radioactive isotopes which are detrimental to the health of animals and plants and human beings alike. Waste products can be used in nuclear weapons, and accidents such as occurred in Chernobyl and Fukushima can contaminate large areas. The upside, though, to nuclear energy is nuclear fusion. And we're going to start with the idea of nuclear fusion in stars. So nuclear fusion in stars is where nuclear energy is released when small nuclei combine to form larger ones. And this process occurs in the cores of stars and is only possible at very high temperatures and pressures, which is probably the only downside, and which have not yet been reproduced sustainably. If to get fusion to come on board, you need high temperature and pressure. That is going to cost government a lot of money. That is why they say it can't be done in a sustainable manner. You have, and it goes with the saying, to get some, you have to give some in a cost. If you have to put high temperature, high pressure to get large amounts of energy, could you imagine? Would the product outweigh the cost? As in, if I pay a lot of money to produce so much energy, would producing so much energy outweigh how much I had to pay to get it started in the first place? Would the energy produced be so great that we could use it for the next 10 years without wondering, having to do this constantly? I think so, because look at the sun. This is exactly what happens on the sun. So it says here, what is a nuclear chain reaction? One where parent nuclei produces daughter nuclei. So one where parent nucleus produces daughter nuclei, and the daughter nuclei then produce more daughter nuclei, which come into contact with each other, and it then forms a chain reaction. Now we have a sugar cube has a mass of 12 grams. How much energy is equivalent of this mass? So again, here we just use E equal to mc squared, and we put 12 over 1,000 times 3 times 10 to the 8 squared, and we know this is in kilograms and this is meters squared over seconds squared. Should I do it like that? Is it understood? I'm just going to say that we multiply that already. So that will give us that times 9 times 10 to the 16. That'll give us 1.1 times 10 to the 15 joules. Yeah. Now it says research the advantages and disadvantages of nuclear energy. Write a report arguing for or against construction of a power station on your island. So I'd like to hear some of those reports. So you could put it down in the comment section. It doesn't have to be too long, but you could put it in the comment section. I would read them. And it says find out what went wrong in Chernobyl and Fukushima and how long it will take to clear up the contaminated land. This you could do on your own as well as a little pet project, a self-enhancement project. So when you come to this section in your schoolwork, you would already be acquainted with the work that's necessary. And that's the end of it. But we need to go back to this. This will take a while because I don't have my actual good calculator with me. So first of all, we have to work out the mass before and the mass after. So before, so we're working out before. Working out before, and 235 would be 3.902996 times 10 to the negative 25 kilograms plus 1 neutron, 1.674927 times 10 to the negative 27 kilograms. And then the mass after would be barium. We have one of barium, that's 2.3899897 times 10 to the negative 25 kilograms plus krypton, which is 1.493157 times 10 to the negative 25 kilograms, plus 2 of these, so we're going to say 2 times 1.674927 times 10 to the negative 27 kilograms. And see, they're already in kilograms, so we could do the calculation now, and we don't have to convert to kilograms. Already in kilograms. For my calculator, get you one of these. 3.902996 times 10 to the negative 25. Plus, don't forget to use your brackets, because some calculators they don't make it easy for you. Okay, so this will give us 3.919745227 times 10 to the negative 25 kg. And then the next one will be, we'll do multiply times 1.67192 times 10 to the negative 27 plus 2.389897 times 10 to the negative 25 plus 1.493157 times 10 to the negative 25, and that gives us 3.9165525 times 10 to the negative 25. So this has less mass than this, as we said, that the before mass is always more than the after mass, because remember, a lot of energy comes off. This explains the energy that comes off, right? So to find delta M, we're going to subtract the after from the before, the 3.919745527 times 10 to the negative 25 minus 3.916555254 times 10 to the negative 25. I'm going to put kilograms on the outside, guys. Right? And once you get the answer, we can find delta E. So whatever answer that is, let's do that now. 3.919745527 times 10 to the negative 25 minus 3.916555254 times 10 to the negative 25. And we get 3.19273 times 10 to the negative 28. I hope this is correct. Times 10 to the negative 28 kilogram times 3 times 10 to the 8 times 3 times 10 to the 8 so we're going to put in brackets times 3 times 10 to the 8 meters per second squared equal to 2.8 7, 3, 4, 5, 7 times 10 to the negative 11 joules. Let me look in my book and see if the answer is correct, because it's so easy to make these mistakes. Yeah! For once in my life, it came out correct on the first try. So get yourself a study guide as well. It's imperative you get one so that you could keep on track with your studying and you don't fall behind. I prefer these over the textbooks for kids because, let's face it, students and people in general, they don't really like to read, and they prefer to read something thinner than something big. And also it's concise, so if you're studying, you could get the textbook. Mind you, I'm not telling you not to get the textbook, I'm just saying as a precursor to reading the textbook, read this one first, and then so that you can get your appetite wet, and then you can go into the textbook after. What I find, some people learn different ways to, the majority of my students prefer reading this and then looking in the textbook to get what do you call it, for understanding. So they want clarity, so they read this and then read the textbook so they get clarity, right? And sometimes they only read this, and then there are the smaller percentage of my students, they would actually read the textbook before they read this. And there are some that don't even read this at all. But you could get the textbook, you also get this to make sure you pick your poison wisely. Anyway guys, this is the end of Physics of the Atom. I hope this helped. See you around. Good luck. Alright, bye.